Hello everyone, welcome back to your favorite and India's most affordable learning platform, Physics Wallah. So in the last session of mechanical properties of fluids, so we discussed about the concept of Archimedes principle, right? So the law of flotation, Archimedes principle, so upthrust and buoyancy, all these concepts we covered in the last session. So and I gave some questions as homework for you. So hope you guys already did those questions. If not, I am going to solve them in today's session. If you are not getting, just follow the solutions which I am going to present here. Okay, chalo. So today's targets. So first we'll go for the homework questions, and then later streamlined and turbulent flow, and equation of continuity, and the Bernoullis principle. So these are our three main objectives for today's session. Okay, so I just need your attention, guys. So spare 1 hour with me, so avoid all the disturbances around you for the next 1 hour, and at the end of the lecture it's very important to prepare your own short notes. And the JEE, NEET, the other competitive examinations are also around, so you guys have to gear up your preparation. So if you are in class 12th, complete class 11th backlogs, whatever that you have, and practice the questions, prepare your own short notes and do revise daily. And class 12th also the same thing, and focus on high weightage chapters. Like when it comes to physics, so focus on modern physics, focus on heat and thermodynamics from the class 11th, and easy and high weightage chapters, these are all. And electrostatics, right? And then electromagnetic waves, one question is for sure in JEE mains. And then we have SHM, easy chapter, and then we have mechanics. So if you are feeling some chapter difficult, so just understand the concepts clearly first, then practice the questions. So when you are practicing the questions, don't take the tough questions in the starting. So start from the very basic question, okay, and increase the level. So step by step, so that you will be able to solve the questions on your own. Okay, clear, guys? And very importantly, you should solve the previous year questions. So if you are ignoring the previous year questions, so you are doing a blunder. Okay, solving previous year questions after the chapter completes is very important. Okay, clear? Chalo. So I'll not take much of your time, so let's get into the topic. Chala. So with very high positive energy, let's begin with the homework questions of last session. So here the first question. So what's the question says? A boat having a length of 3 meters and a breadth 2 meters is floating on a lake. Okay, so then the boat sinks by 1 centimeter when a man gets on it. So the mass of the man is, so they are asking what is the mass of the man. So the question is written in the simple language. Hope you understood the question. What we have to find first, what is our objective. So let's suppose we have the boat here like this. Okay, so when a person gets on it, so what happens? So the boat sinks by 1 centimeter. So the boat sinks by 1 centimeter, let's suppose. That's what they said. And length and breadth of the boat is also given. See, when the person gets onto the boat, so the boat still floats, like it sinks 1 centimeter, but it's floating on the water only, right? So it will not completely sink. That's the main concept. So at certain time, after some time, it comes to equilibrium. Once a man get into the boat, so what happens after some time? So it sank by, let's suppose, 1 centimeter, then it is going to be in equilibrium. So in equilibrium, so the upthrust and its weight, so they both will be balanced. So the water will show upthrust, yes or no? So there will be some upthrust, and then so the weight, these both will be balanced. So U is equals to M into G. So now we have to find what is the mass of the man. So this is the mass of the man, M we have to find. So what is this upthrust? So upthrust formula we know that VF rho F G. Yes, so which is equals to M into G. So just follow the basic calculations. So what is the volume of the boat? So the length of the boat is given and breadth of the boat is given and the depth, so by which it sank, which is 1 centimeter. So here the volume of the fluid is nothing but volume of the solid displaced or the volume of the object displaced. Yes or no? Volume of, this is what is the fluid? Volume of the fluid immersed, volume of the fluid displaced or I can write it as volume of the solid immersed. So volume of the solid immersed is nothing but the boat volume. So here the boat volume which is inside the water. So we know the length of the boat, which is 3, and we know the breadth 2, and we know the height, so which is 1 centimeter. I am writing 1 by 100. So simply substitute the values now. So here it is 3 into, so 2 into, so 1 by 100 because it is given in centimeters. These two are in meters, guys. And then, so what is the density of water? What is the density of water we take? So let's take 10 to the power 3 into G. So let's cancel G on either side better. So that's it. So we got the mass value. So the mass will be equals to 2 zeros, 1 0 cancel, 6 into 10. So 60 kg. So the man weight should be 60 kg. So the option 1 is the correct one. Done, guys. Simple question. Chalo. So let's move on to the next question. A tank contains water on top of mercury. So here this is the tank. So there are two liquids which are there. So what are they? One is mercury at the bottom because its density is high. You remember the density of mercury, right? So which is 13.6 into 10 to the power 3 kg per meter cube. So whereas water has, so the density 10 to the power 3 kg per meter cube. As the density of mercury is more and density of water is less, so we can say that, so mercury settles at the bottom in the container and water on the top. These two are immiscible liquids. Yes or no? So they two do not combine. Okay. So a cubical block of sides 10 centimeters. This is a cubical block of side 10 centimeters is in equilibrium. Inside the tank. So the depth of the block inside the mercury is, so we have to find, so by how much depth, so the mercury is inside the, the block inside the mercury liquid. So its total length is what? So 10. So if it is x, I can consider this as 10 minus x. Yes or no? So this is 10 minus x. So simply first there are two liquids. So we don't know, for one liquid we can easily write the formula. So now there are two liquids. Understand the concept carefully. So we are going to derive one general formula also from here. So let's understand carefully. Here the mercury will create the upthrust, right? So the mercury will create the upthrust. So this is the upthrust by the mercury, and so the block is there in the water as well. It is there in the water and it is there in the mercury. Yes or no? So the water also exerts upthrust, right? So which will be equals to, so the weight of the block. That's it. So this concept if you understand, so you can solve the question easily. It is in equilibrium. So at equilibrium condition we can write like, so the upthrust by the mercury plus the upthrust by the water is balanced by the weight of the block, weight of the cubical block. That's it. This is the formula. So now, so what is the upthrust formula? We know the upthrust is equals to rho F VF G here. So coming to the upthrust by the mercury, which is nothing but density of mercury, just write the formula, and volume of mercury into, so the G plus, so what is the upthrust by the water? So the density of water, volume of water into G is equals to, here in place of M, so density of solid, volume of solid into G. That's it. So here I can write G gets cancelled. So then rho M Vm plus rho W Vw is equals to rho S Vs. So this is one general formula. So if there are two immiscible liquids, so we can write the formula this way. So you can simply remember this way, this part. See here. So if there is only one liquid, we can write it right. So rho FVF is equals to rho SVS. Yes. But if there are two liquids, so rho, I'll write, if there are two liquids, you can write rho 1 V1 plus rho 2 V2 is equals to rho SVS. Liquid 1, liquid 2. So here, as a mercury and water are there, I am writing M and W as the denotions. But if there are some other liquids, 1, 2 are there, unknown liquids, so you can write rho 1 V1 plus rho 2 V2 is equals to rho SVS. So if there are more liquids, 3 liquids are there, let's suppose, rho 1 V1 plus rho 2 V2 plus rho 3 V3 is equals to rho SVS. Okay, if one liquid is there, this is the formula. Where is that? So if one liquid is there, rho S VSG is equals to rho F VFG. If one liquid is there, or rho SVS is equals to rho F VF. So G also you can cancel, one liquid. So if more than one liquid are there, so then just add in terms of the fluid, add it here. So 2 are there, 3 are there, so your wish. Then, and you can also write this formula in terms of heights also. So how do we write in terms of height? See here. So the density of the mercury, let it be M, and so the cross sectional area into the height of the mercury into plus, so here density of water, so the cross sectional area into the cross sectional area of that cube is going to be same. So into, so the height of the water, so which is equals to rho SVS. So that area, sorry. So here we can write, so rho S means, so the cross sectional area of the solid into, so the height of the solid into the rho S, right? So here area cancel. So we get, so the rho M HM is equal plus, so rho W HW is equals to HS rho S. So this is a concept. Clear guys? Understood? So previously we have seen rho SHS is equals to rho SHS is equals to rho FHF. Previously one liquid is there. So here two liquids are there. So just I am writing with the denotations. So this is the general concept you can apply when there are more than one liquid in the concept. Done? So now you can solve this question. What they are asking? So what is the depth of the block inside the mercury? So you can, height they are asking. So you can use this formula. So here, do we have another slide? Yes. So let this height be x, and this height will become 10 minus x, obviously. So the total height is 10, right? Yeah, good. So now I can write, so the rho of mercury into, so the height of the mercury plus, so rho of water into the height or in the water is equals to, so rho into rho of the solid into, so the height of the total solid. So simply substitute the values. So rho M, mercury value 13.6, right? Yeah, so mercury has 13.6 into, so the height in the mercury, let it be x. So the height in the mercury, let it be x. So rho of the water, see, it is relative density. So our specific gravity in gram per cc you should take. So that's why density of water I am taking 1. So then what else? Height in the water. So in the water it is 10 minus x is equals to density of the solid. In the question they gave, yeah. So 8.56. So into HS, height of the solid. What is the complete height of the solid? 10 centimeters. So everything is centimeters only. So don't worry. Clear? So this is we have taken in gram per cc. This is relative density or specific gravity. So this one also in centimeters. This one also gram per cc or relative density or specific gravity. So this one is also in centimeters only. So now let's calculate. So 13.6x plus 10 minus x is equals to 85.6. So just multiplied with the 10. So here 13.6x minus x. So 12.6x is equals to 85.6 minus 10. So here 12.6x is equals to, so 75.6. Yes. So from here x is equals to 75.6 by 12.6. So which I can write it as 756 by 126. right? So what is 126 5 times 72 means 6 times you can check. So 36 12 15 6 7, so yes, so exactly 6 times it goes, so which means 6 centimeters is a correct answer. Done. Option 1. So don't take the approximation values because the options are very close, 6 7 8 like that, 5 6 7 8. Done, guys. So this concept you should remember, this is a concept actually here, whatever we dealt, this is a concept. Okay, so this is applicable when there are two immiscible liquids are there. Done. Good. So now let's move further. So we have got one more question, so try to solve this question on your own. First read the question. So what's the question says? A metallic sphere floats in immiscible mixture of water, density 10 to the power 3 kg per meter cube, such that its 2/3 part is in water and 1/3 part is in the liquid. So the density of the metal is, so they are asking what is the density of the metal. Let's say this is a container. So in this container there are two liquids. So one is some unknown liquid, the other one is a water. So consider this is a water. So now the sphere is there in such a way that, so such that its 2/3 part is in the water. So let me take a sphere here. So its 2/3 part is in the water, and then 1/3 part is in the 1/3 part is in the liquid. Sorry, my bad, reverse, I wrote reverse. So 1/3 part is in the liquid and 2/3 part is in the water. Let me write the diagram properly. So this is a liquid. Consider this light yellow color is a liquid, and then so this part is a water. So now see here. So it is in water it is more, right? So 2/3 parts, yes. So in water it is more, and in the liquid it is 1/3, and in the water it is 2/3. So this is water here. Yes, fine now. So there are two immiscible liquids. So fine. So the density of the metal is. So we can simply write. So there is liquid density of the liquid into, so the volume of the liquid plus, so the density of water into the volume of water. Yes, the same formula you can apply. So the density of the mercury plus volume of the mercury plus the density of water plus volume of water. Here there are two liquids, density of liquid plus volume of liquid, and here volume of water is equals to rho s Vs. That's it. So now you can solve the question. You can solve it easily, right? So just calculations. So what is the density of the liquid, what is the volume of the liquid, and we have to find what is the density of the metal. So this rho s we have to find. This rho s we have to find. So just substitute the values. Do it fast, guys. So I'll give 1 minute time. So do it fast. Do the calculations on your own. Done. Done. See. So here, so what is the density of the water? So 1000 into, so what is the volume of the water? In water it is 2/3, and then so what else is there? So here in liquid, what is the volume of the liquid? So 1/3 into, so what is the density of the liquid? So they did not give. So is equals to, so what is the density of the solid? We have to find. And what is the volume of the solid? So let it be 2/3 1/3. So I am considering it as 1. So now the only unknown we have here, it is this one. So the rho s. So calculate for the rho s now. Calculate for the rho s. here the liquid, okay, so rho L also we don't know, no? So liquid density also should be mentioned. So take some random value, guys. Liquid density, so here it is not mentioned in the question, I guess it's a misprint. So liquid density, so just to take some random value x, okay, so that value also will be given, and then you have to just find the rho s value, okay. So just find the rho s value, so it will be done. So you can do that on your own, because this value also will be given in the question. Chal. So just substitute the values and leave the option, because here this value is not given. So after the class I'll check and I'll update here, take it as a homework, okay. So in the next class I'll update this one, what is the density of the liquid, I'll check and update, so you can do it as a homework, okay guys. Chal. So next we have one more question. So what's the question says? Two non-mixing liquids of densities rho and n rho are put in a container. So the height of each liquid is h. A solid cylinder L and density d is put in container. So the cylinder floats with its axis vertical and length rho L in the denser liquid. So the density d is equals to, yes, see here. So don't worry, it's a simple question only. See, actually we check the PPT. Once it is delivered from the DTP operator, we check it twice. But still sometimes these kind of information will be missing. Like it's a technology issue, because they also will be hurry. They also have lot of work, DTP operators. So some mistakes might happen like this sometimes, okay. Chalo. See, let's go for this concept. So there are two non-mixing liquids of density rho and n rho. So one is of n rho. So let this liquid has density n rho, fine. So and the another one has a density so this is of the density rho, fine, are put in a container. The height of each liquid is h. So the height of each liquid is h. So this one is of height h and this one is of height h, fine. So a solid cylinder of length L and density d is put in this container. So a solid cylinder of length L, and so this is the total length L. So understand carefully, this is the total length of the this one L, and this has total density d, fine. Now is put in this container. The cylinder floats with its axis vertical and the length rho L. So the cylinder floats with its axis vertical and length rho L in the denser liquid. So the denser liquid is this one. So in this one the length is rho L. Now what will be this length becomes? This length becomes, the total length is L. So this length will become L minus rho L. L minus rho L. So that's it. So we have got the enough information. So now you can go for the calculations. So there are two immiscible liquids. I can write the formula. Rho 1 V1 plus rho 2 V2 is equals to rho S Vs, the solid S. Yeah. Now what is rho 1? The density of the first one. So let's write n rho. So the density of the first one n rho, or else let's do this way. In terms of cross sectional area, shall we write? So here the cross sectional area is A. So let's write. So the A1 H1, the cross sectional area is same for all. So A H1 V1 plus A H2 V2 is equals to, so this one rho means A H total height into, so the Vs. So rho S into A H, the total height, let it be H. So then I can write here A gets cancelled. So the H1, what is the height of the first one? So let it be H. The height of the first one is H, because each liquid is of height H. So what is the volume of the first one? What is the volume of the first? density, my bad, sorry guys. See here, density same here, A into H1 in place of volume, here density rho 2, so here A into H2 is equals to, so the density of the solid, let it be, and here A into the total height. So here cross sectional area gets cancelled, so rho 1 H1 plus rho 2 H2, direct formula this one actually, so rho S into the total height. So here what is the density of the first one? I am considering this is a liquid one, this is a liquid 2. So the first liquid has rho L, N rho is the density of the first liquid. And what is the height in it? So the height in the first one is, so rho L. So this is rho L plus, so rho 2. So what is the rho 2? The density of this one is rho into, so the H2. So what is the height in this? So L minus rho L, So then which is equals to, so rho S, let it be rho S. So then the total solid density only we require, right? In the question they mentioned it as D, so let's take D only. And H, so let the total height be H only. Let the total height be H or L they mentioned. L, let's take the total height is L of the solid cylinder. So now we need what is D. So simply what you do is, so N rho square L N L plus here rho L minus, so rho square L is equals to DL. So now do we have another slide? No. See here. So again I am writing the condition, the same one. So rho square NL plus rho L so minus rho square L is equals to DL. So L gets cancelled. So we need the D, right? So the D is equals to, so check the options. So we can take rho common. So rho you can take common. So this is going to be rho N, here rho N plus rho minus 1, sorry, plus 1 minus rho. Yes, yeah. So now D is equals to rho into, so let's write 1 plus rho N minus rho. Just proceed according to the options. So rho into, so 1 plus, here again rho take common, so N minus 1. So this is the final answer. Check this one. So rho into 1 plus N minus 1 into rho. So rho into 1 plus N minus 1 into rho. Option 2 is the correct one. So the concept is simple. So just adjust with the terminology, guys. So the terminology is important. That's it. So the concept is going to be very simple. Done? Clear, guys? Chalo. So now, so then what is the condition for limiting condition for the floating? So we have seen if the density of the solid is greater than the density of the fluid, so it sinks completely. Right? So which means, so what does it mean by complete sinking? So here this is a container and then here we have the liquid. So if there is any object whose density is greater than the density of fluid, this is the density of solid, and let's consider this is the density of fluid. So your density of solid is greater than the density of fluid, it sinks completely like this. And then we have also seen one more condition. So what is that? So the rho S is less than that of the rho F. So where, so the body floats, right? Object floats. So now, so in this particular case, how it floats, let's suppose this is one liquid. So half of it's, not half of it exactly. So depending on the density of the liquid, so like this, some part of it will be floating and some part of it will be sink. Okay. So now what if the third condition, what if the rho S is equals to rho F? So what is rho S is equals to rho F? The densities of solid and the fluid both are equal. So this is a limiting condition for floating. This is the limiting condition for floating. Clear, guys? Chalo. So now here how the object sinks. See, So consider this is a container, here the object liquid, and the object will be sank like this. So just below the surface, this is a limiting condition for the floating. Understood, guys? Clear? So with this we have completed so the floating concept. So everyone understood what is law of floating and the concepts of floating? Is this concept clear? Chalo. So now let's go for the fluid dynamics part. So we are going to discuss the fluid dynamics part where the fluid flows. Okay. So here in the fluid dynamics, especially we are going to deal with so the equation of continuity, and then so the Bernoullis principle. Bernoullis principle, and we'll also study the velocity of efflux. Velocity of efflux. So and then we'll see what is Reynolds number in today's session only, and so how to solve the questions based on Bernoullis principle. So this Bernoullis principle is applicable on only the fluid dynamics? No, it's applicable for the fluid static fluids and the dynamic fluid. So for the fluid statics as well as for the fluid dynamics. So it is applicable for fluid statics and fluid dynamics. Okay, clear guys this part? Chalo. So now, so let's go for the theory part. So some theory part we'll see first, then we'll go for the questions. Okay, chalo. So understand the concepts clearly. We are going step by step here. So first, what is steady flow or streamline flow or the laminar flow? So all are same. Okay, there are actually two types of flows in a fluid. So one is the laminar flow, the other one is the turbulent flow. The laminar flow is also called the streamline flow or the steady flow. So this streamline flow or steady flow is nothing but, let's suppose a fluid is flowing through this tube. Consider this is a tube. So a fluid is flowing. Okay. So the velocity at a given point for a given particle is constant. So then that flow is said to be the steady flow or the streamline flow or the laminar flow. Let me repeat again with the example. So let's suppose, so from this point, let's suppose if I consider this point, so a fluid particle is moving with a speed of 10 meter per second, and so the particle which is coming later, so that also should move with the same 10 meter per second, and every particle which is moving from this point, so should have same 10 meter per second. Okay, so the particle at other place might have some other velocity. Okay, here to here the velocity might change, but all the particles which are passing through this point 1 should have the same velocity, which is 10 meter per second. Example I am saying. Let's suppose here the velocity is 20 meter per second. So all the particles which are passing through the point 2 should have the same velocity here. So that flow is called the streamline flow or the steady flow. So the streamline flow or steady flow or the laminar flow, it doesn't mean that the velocity has to be same throughout its flow. At a given point, its velocity of every particle should be constant. That's it. Okay. So that's what I wrote. The path followed by a fluid particle in steady flow is called the streamline. So velocity of fluid particle at any point of the streamline is along the tangent to the curve at that point. Okay. So here, so the velocity for a fluid particle, the velocity for the fluid particle at a given point, should be constant. At a given point should be constant. The velocity for a given fluid particle, at a given point should be constant. Here all the particles of fluid should have 10 meter per second. Example. And here they should have 20 meter per second. So let's suppose here if it is a velocity is 30, so all the particles which are passing through this point should have the 30 meter per second. Then it's called the laminar flow or the steady flow or the streamline flow. Definition is clear. And one more thing, so if you want to find what is the direction of that streamline flow. So at that point, so just draw a tangent, the tangent drawn on the curve. So here, see, so velocity of fluid particle at any point of the streamline is along tangent to the curve at that point. So if you want to know what is the direction of the streamline flow, so just draw the tangent at this point. And then if you want to know here, so just draw the tangent. So the tangent gives the direction of the streamline flow. Okay, so the tangent on curve, gives so direction of streamline flow, so the streamline flow. Clear, guys? Chal. So now, so the next one is a steady flow or the streamline flow or the laminar flow, the same thing. So the flow of the fluid is said to be steady if at any given point the velocity of the each passing fluid particle remains constant in time. So that's what we discussed now. So the velocity at a given point should be constant with the time. So this does not mean that the velocity at different points is same. So here the velocity, here the velocity, here the velocity may be equal or may not be equal. So there is no compulsory condition that the velocity here and here should be same. But the velocity passing through this point, the velocity of each particle which is passing through this point should be same. And velocity of each particle passing through this point should be same. That's it. So but here velocity may be or may not be equal. Done. That's the second point I wrote. So that is, so at some other point the particle may have different velocity, but every other particle which passes the second point behaves exactly as a previous particle that has just passed that point. Let's suppose here one particle has passed, so it passed with 10 meter per second from this point, and the particle which is coming, the next particle which is coming to this point should have the 10 meter per second. Then only it's said to be the streamline flow. Clear? Sure. So the theory part again. So the next, in streamline flow, no two streamlines can cross each other because the tangent drawn on the, so I'll write here only. So because let's suppose this is one streamline flow and this is one streamline flow. So if these two intersect each other at the point of intersection, so the streamline direction for this one, this side, and for this one, this side. So at the same point, at the point of intersection, the streamline flow has two directions, which is not possible. At the point of intersection, if you draw the tangents, the streamline flow indicates two directions, so which is not possible. If they do so, the particles of the fluid at the point of intersection will have two different directions. See here, two different directions, so which will decrease the steady nature of the liquid. So it's not said to be the steady flow anymore. Okay. So the greater is the crowding of streamlines at a place is greater the velocity of the liquid particles at that place. So vice versa. So let's suppose here, so if crowding of streamlines is more, here the crowding is more, here the gap is more, right? So let's say, let this be point A and this be point B. So the greater is the crowding of streamlines at a place, greater is the velocity. So here the velocity at A will be greater than the velocity at B. Done, guys? Clear? Sure. So simple theory points. So direct questions can be picked directly from here. Okay. So streamline flow is possible only if the liquid velocity does not exceed a limiting value. So that means for a limited value, for the low speeds, at low speeds only you can achieve the streamline flow. So at very high speeds of the fluid, so the streamline flow is not possible. Okay. So steady flow is achieved at very low speeds. That's what they wrote. Beyond a limiting value called critical speed. After the critical speed, so this flow loses steadiness and becomes turbulent. So turbulent means at a given point the velocity varies continuously. Streamline means the velocity at a given point for a fluid particle is going to be constant. For all the fluid particles passing through that a given point is going to be constant. Understood this difference? What is the turbulent and the steady flow? Clear? Chalo. Next. So in rivers and canals where the speed of the water is quite high, or the boundary surfaces cause abrupt changes in velocity of the flow. So then the flow becomes irregular. Such flow of liquid is known as a turbulent flow. So see the simple theory. So in rivers and canals, so you can see the abrupt changes in the velocity of the liquid, right, fluid. So that flow of the liquid is called the turbulent flow. So thus the flow of fluid in which velocity of all particles crossing a given point is not same. Okay, so one particle is crossing some point here, let's suppose. So let me take this diagram. So one particle crossing this point has some 10 meter per second. The next particle has 20 meter per second. So and the next particle has some 15 meter per second. So like that, each particle passing through a given point is not having the same speed. So in that case, so the flow is said to be the turbulent flow, is not same, and the motion of the fluid becomes irregular, so or disordered. So this is called the turbulent flow. Clear? So simple theory part. Next, so here NCERT diagrams, so you can see the diagram. So some streamlines for the fluid flow. This is the streamline flow you can observe. So here you can see, so the this is the turbulent flow, a jet of air striking the flat plate placed perpendicular to it. So this is an example of turbulent flow at different points. So the different velocities will be there for this. Clear? Sure. So then let's go for the Reynolds number. So first, what Reynolds number says, what Reynolds number indicates. So it explains the nature of the liquid. So whether it is turbulent or the streamline, whether it is turbulent or streamline flow. So just a bit. Okay, so the Reynolds number is given by rho v d by neta. So it tells us, so whether the liquid flow is turbulent or streamlined or steady flow. So it's a dimensionless number. Remember, it's a dimensionless number. So if R value, if it is less than 1000, so then the flow is said to be the streamline flow. If R value is greater than 2000, so then it's said to be the turbulent flow. Turbulent flow. Okay, clear guys? R is less than 1000, so streamline flow. R is greater than 2000, so turbulent flow. So what about between 1000 and 2000, sir? So it's uncertain. We can't say it's a streamline flow or the turbulent flow. Clear, everyone? Everyone? So chalo. So what are these values, sir? This is the density, this is the velocity, this is the diameter of the tube, this is the viscosity. So where rho is the density of liquid. Write down. And then, so v is the velocity with which it is flowing. And then let's suppose it is flowing in a tube. So then d is the diameter of tube. Done? Yes. So then we have, so neta is a coefficient of viscosity. So coefficient of viscosity. Again, we are going to discuss about this in the upcoming classes. Okay. So this is the coefficient of viscosity. So Reynolds number is a dimensionless number. So no M0, L0, T0. So the dimensional formula. Clear? So like a coefficient of restitution. So and like a what's that? Refractive index. So this is also the dimensionless quantity. Done guys? This part is clear? Chalo. So now let's go for the equation of continuity. So what does it mean by equation of continuity? This equation of continuity is applicable for the steady flow. So the equation of continuity is applicable for the steady flow or the laminar flow or the streamline flow. So let's suppose this is a tube which is having different cross-sectional area. So then, so a fluid is passing through this tube. Then, so we can write as the equation of continuity says that the mass per unit volume entering is equals to, so the mass per unit volume leaving the cross section. So the mass per unit volume entering the cross section is equals to, so the mass per unit volume leaving the cross section. Unit volume leaving the cross sectional area. So mass per, let's suppose this is 0.1, this is 0.2. So the mass per unit volume entering and the mass per unit volume leaving. So that means, so here this is applicable for the ideal fluid, guys. We are talking about the ideal fluids, so which are incompressible and non-viscous. So incompressible means the density is same, yes or no? So which are incompressible and density non-viscous, no shearing force, no frictional force, and no tangential force. That's called the non-viscous in nature. So incompressible means the density same. Here the density same. Clear? So how much amount of the fluid that is entering here, the same amount of the fluid that is leaving here. That's what equation of continuity says. Okay, so what is the mass per unit volume? So here we can, the mass entering per unit volume, which is nothing but the density, or the, let's write only the mass entering. Let's write, so the mass entering, not per unit volume, just write. So the mass entering the given cross section is equals to, so the mass leaving the given cross section. So whatever the mass that is entering at this cross section, the same amount of mass is leaving at the cross section too. Clear, guys? So now what is the mass formula we can write? Mass of what? So you can write fluid. Okay, so of fluid, mass of fluid entering. Let me write the statement properly. Mass of fluid entering is equals to, so if you want you can mention the time also, let's say per second. So and the mass of fluid leaving per second. Mass of fluid leaving per second. Mass of fluid leaving per second. So now you can write the mass formula there. So what's the mass? So the mass is equals to the density into volume. You can write. So you can write the mass is equals to density into the volume. Yes or no? So here the density into, so the volume. So here I'll write, so the cross sectional area A1 V1 is equals to, so there I write, so the density is going to be same because we are taking the incompressible liquid. So which is A2 V2. So rho gets cancelled. So the A1 V1 is equals to, so the A2 V2. So this is called the equation of continuity. So note this down. So very, very important. So this equation of continuity, we are going to use it throughout the Bernoullis principle, guys. Done? Done? Clear? So density into, so why A1 V1, sir? Because it's a volume entering per second. A1 V1 means volume entering per second. So volume entering per second is nothing but the cross sectional area into the velocity at that point is equals to, so the cross sectional area into the velocity at this point. So A1 V1 is equals to A2 V2. So this is the equation of continuity. Done. So now the equation of continuity for a compressible liquid. So compressible liquid means density is varying. Compressible liquid, if it is a compressible liquid, so the density is not same. Density is not same. Right? So chalo. So I can write here. So here the density, let it be rho 1. Here the density rho 2. So then it becomes rho 1 A1 V1 is equals to rho 2 A2 V2. So this is a concept. So if the density varies, compressible liquid means the density varies like this. Done. So now, so the volume of rate of flow. So what does it mean by volume of rate of flow? So the dV by dt, which we call. So what is that? The volume of rate of flow. So how much volume per time? Rate means per time, right? So how much volume flowing per time? So what you can write here? So what is the volume flowing for the second? Volume that flows in 1 second, you can write simply, guys. Volume per second. See. So actually it is denoted with Q. So the Q is equals to dV by dt. So which is nothing but, so volume of fluid flows in 1 second. So which is nothing but, so in 1 second means A into, so let the velocity be V, which is AV. Okay. So in this equation of continuity, so you can write A1 V1 is equals to A2 V E2 means, here you can also write AV is the constant. That's it. In the question, if they ask what is the volume of rate of flow, so you can simply write, so the AV. Okay. Let's suppose this is a tube. So from this tube, some fluid is flowing. So in 1 second, in t is equals to 1 second, so we can write, let this one is moving with a velocity v. So then we can write like, so what's the distance? So the distance is equals to speed into time. The distance is equals to speed into time. Right? So with what speed it is moving? V speed. So in what velocity? A. In time 1 second. So which is nothing but distance is V. So we can write, so in 1 second how much volume it flows? So the volume is equals to A into, let's suppose it covers a distance D in the 1 second. So which is nothing but A into D, right? A into D. So in place of D, the distance, we can write the velocity V. That's what I wrote here and here also. So the A1 V1 is equals to A2 V2. Understood, guys? Clear? So this is a concept. So the volume of rate of flow means AV it is. Chalo, good. So now we have got one question. So let's try this question on your own, everyone. Let's try this question. Water is flowing through two horizontal pipes of different diameters. So which is connected together? So the diameters of the two pipes are 3 centimeters and 6 centimeters respectively. If the speed of water in the narrower tube is 4 meters per second and the speed of water in wider tube is, see here. So this is a wider tube and this is a narrow tube. So they both are connected like this. Okay, chalo. So then the obvious thing is that, so if it is narrower, the velocity will be more. If it is wider, the velocity will be less. That's why whenever you close the pipe with a thumb, so what happens? The pressure will be more, the velocity of the water will be more. Yes or no? So here if the narrower is of 4 meters per second, so the wider one will have obviously, so less than that. Sorry, more than, less than that. Yes or no? Narrower one will have the more speed and wider one will have the less speed. So obviously you can cancel 16 and same speed also not possible. Either 1 or 2 is the correct answer. So then you can use a formula. So we can write, so equation of continuity, A1 V1 is equals to A2 V2. So then use a formula. So what is A1? The cross sectional area of the first one. So let's take the circular cross section, pi into, so r square. So the first one diameter is 3 centimeter. The larger one diameter is 6 centimeters, right? So 6 centimeters means 6 by 2. So let me write 3 centimeters whole square into, so this one velocity V1, wider one we have to find. So A2, so pi into, so its diameter is, its radius is 3 by 2 whole square. So into the velocity V2, so which is 4 meter per second. Here centimeter gets cancelled, centimeter square gets cancelled, don't worry. So here pi gets cancelled, so here 3 square gets cancelled. Send this 2 square 4 to this side, so which will become 4 gets cancelled, 1 meter per second. Simple calculations. So we have got 1 meter per second. Here 2 square means 4, 1 by 4, 1 by 4, 1 by 4, 4. They both get cancelled, we get 1 meter per second. So option 2 is the correct one, guys. Done. Simple question. Chalo. So let's move further. An incompressible liquid is flowing through a horizontal pipe as shown in the figure. So the value of speed V is, see here, same concept. So the AV should be constant. So the A into V should be constant. So what does that mean? Here the cross sectional area. So what's the cross sectional area here? A into, so the speed 8 is equals to, let's write here the cross sectional area again 8 into, so what is the speed here? 6 plus here the cross sectional area 3A. Yes, sorry, here the cross sectional area is 0.8A. Here 0.8A cross sectional area into the velocity there 6 plus here the cross sectional area 3A into the velocity here V. So then what we can cancel? So A gets cancelled. So we actually need what is V velocity, the value of V. So simply this comes out to be, so 0.81 times, don't do that. So here 8 is equals to, so 0.48 plus 3V. Yes, so chalo. So then 3V is equals to 8 minus 0.48. So 3V is equals to 7.52. So the V is equals to 7.52 by 3. So in 3 ones are 3, 2s are, and then 1 5, 3 5s are, so 2.5 something like that. So approximately, so we can go for anything calculation mistake, no, right? So A into the cross section velocity is 8. So the cross sectional area is 8 here, A here. So A into 8 is equals to 0.8 into A. So 6, yes, speed here 3A cross sectional area into the velocity V. So find 8 here, A gets cancelled. 8 is equals to, so this is 48 means 0.48 plus 3V. Yes, so this is 3V is equals to 8 minus 0.48. So which is 7.52, correct only. So then V is equals to 7.52 by 3. So which comes out to be, so 3 ones are 3, 2s are 6, and 1 5, 3 5s are, so something around 2.5. So but there are two close options which we can consider. Is there any value given wrong? So let's check the calculations again, guys. Check the calculations again. Any calculation mistake I did? So let me do it again. So this is 8 is equals to 0. Sorry, this is 4.8. My bad. This is 4.8. So plus, yeah. So 3V. Now I got it. So 3V is equals to, so 8 minus 4.8. So here it comes out to be, so we can write so 0.23. So 3.2. Yes. So then V is equals to 3.2 by 3, approximately 1 point something we get. So 1.1 we can write, approximately 1.1 meter per second. Option 1 is the correct one. Clear, guys? So the concept is simple. Done? Sure. So we don't need another slide for this. So then we have one more question here. So the cylindrical tube of a spray pump has radius r. So one end of which has n fine holes each of radius r. So if the speed of the fluid in the tube is V, so the speed of the ejection of the liquid through the holes is here. So this is a tube, and then for this tube, so it has some n number of holes. So the liquid is flowing from here. So with the speed V. Yes or no? So then, so what is the speed from this each hole? That's they are asking. So let the speed from this each hole is V dash, and radius of this each hole is small r. Here the Cylindrical tube has radius r. So equation of continuity you can apply. So the cross sectional area into the volume is equals to, here the cross sectional area into, the cross sectional area into velocity is equals to the cross sectional area into velocity here. So I can write, so what's the cross sectional area here? So pi into, so r square, here the velocity v is equals to, here n number of holes are there, n into, so pi into, each one has radius r, so n pi r square into, so the velocity in each is v dash. So simply they are asking what is the v dash they are asking. So pi gets cancelled, so the v dash is equals to, so v r square by n r square. So is there any option like this? So v r square by n square r square, v r square by n r square. Option 3 is the correct one. Direct formula based. If the values are given, you can substitute the values also. Done guys? Chal. So now let's go for the Bernoullis principle. See, as I mentioned earlier, the Bernoullis principle is applicable for fluid statics as well as fluid dynamics. The first point. And then it is based on the conservation of energy. The Bernoullis principle is based on the conservation of energy. Remember that. Okay, done. So now, if we now suppose that an incompressible, non-viscous and irrotational, one more word is adding here. So we know what is incompressible, the density is going to be same, and non-viscous, there is no tangential force, so there is no shearing stress, so or there is no shearing force. So and irrotational, the liquid should not rotate. So is flowing through the pipe in steady flow. So how it should flow? It's a, for steady flow only, it's Bernoullis principle is applicable. Now, so this is a tube which is of some cross sectional area A1 here, and which is of some cross sectional area A2 here. Okay, and this part is at a height of h1 from the ground, and this part is at a height of h1 from the ground. So now the Bernoullis principle says that the pressure energy per unit volume and the kinetic energy and the potential energy per unit volume, so will be constant. So which means, first I'll write the statement, I'll write the formula, so then I'll go for the explanation. So the P1 plus half rho V1 square plus, so rho GH1 is equals to, so the pressure there P2 plus half rho V2 square plus rho GH2. So overall I can say that the P pressure plus rho V square plus rho GH should be constant. So what are these, sir? This is a pressure energy per unit volume. So this is a pressure energy per unit volume. This is the kinetic energy of the liquid per unit volume, and this is a potential energy per unit volume. So this is pressure energy, and then this is a kinetic energy half mv square type. So this is a kinetic energy and this is a potential energy. So these should be constant. That's it. This is what the Bernoullis principle says. So the Bernoullis principle is applicable for fluid statics, fluid dynamics, and it's based on the conservation of energy. So which energies are going to be conserved? So the pressure energy per unit volume, kinetic energy per unit volume, and potential energy per unit volume are going to be conserved. So that's it. This is what you have to remember. Clear guys? Chal. So just note that down, everyone. So first, over. So you can write per unit volume here. If you want, you can write per unit volume. Here per unit volume. So here also per unit volume. Done. Now, so next, so we can also write this as, so the pressure energy per unit volume plus rho v square plus rho gh is going to be constant. So this we also can write it as the total energy per unit volume. the total energy per unit volume should be constant, which is nothing but the conservation of the law of conservation of energy. So this is nothing but the law of conservation of energy. This is nothing but the law of conservation of energy. Done? Clear, guys? Everyone? Chalo. So good. So this part is done. Now let's move further. So now we have different heads. So in this formula, so if you observe, so we have pressure plus, so half rho v square plus and rho GH. Rho GH is going to be constant, right? So now if I divide everything by GH, so if I divide everything by GH, so then we get the different heads. So consider the divide everything by GH there. Sir, GH or rho G, sorry, my bad. So divide everything by rho G, P by rho G plus rho V square by rho G plus, so rho GH by rho G. So here, if you can write here, P by rho G plus rho cancel. So here V square by 2G plus, so here rho G cancel H. So constant. So this is called the pressure head. This is called the pressure head. And this is called the velocity head. This is called the pressure velocity head. And this is called the length head. Okay, done, guys? Clear? So this is done from potential energy, right? Yeah, so you can call it as the potential head. Clear this part? Everyone? Chal. So now if you observe, so all these will have the same dimensions of the length. So the pressure head and velocity head and the potential head. So the P by rho G and so V square by 2G and H. So they all will have same dimensions. They all will have same dimensions as of length. They have same dimensions as of length. Clear? Everyone? So this is a concept. Chalo. Good. So now if the fluid is at rest, so if the fluid is at rest, so what does it mean by fluid is at rest? So the velocity is going to be 0. Yes or no? So then what we can write here formula? So the P1 half rho V square, rho V1 square plus rho GH1 is equals to P2 plus half rho V2 square is plus rho GH2. So if the fluid is at rest, so this term will become 0. So this term will become 0. V1, V2 velocities will become 0. So then we can write P1 rho GH1 is equals to, so P2 rho GH2. So simply I can write it as P plus rho GH is going to be constant. P plus rho GH is going to be constant if the fluid is at rest. Done? Clear, guys? Chal. Good. So now in a horizontal pipe, so in a horizontal, let's consider this is a horizontal pipe. So if I consider this pipe is at a height of, so some h from the ground. So some height h from here and some height h from here. So it is at an equal height. Both the ends are at equal heights, right? Both the ends of pipe, are at equal levels, are at equal heights. So then, so we can write, so what's the actual formula? So we know that P1 plus half rho V1 square plus rho GH1 is equals to P2 plus half rho V2 square plus rho GH2. So here the H1 H2 is equals to H. H1 H2 is equals to H. So then what we can write? So P1 plus half rho V1 square plus rho GH1 is equals to P2 plus half rho V2 square plus rho GH. Sorry, in place of H1 I am writing H only here. So H1 is equals to H, H2 is equals to H. So that this part gets cancelled. So the P1 plus half rho V1 square is equals to, so the P2 plus half rho 2V square. Done? Clear guys? Everyone? Chalo. So this part is also done. So next we have some questions here. So a non-viscous liquid is flowing through a frictionless duct. So cross section varying as shown in the figure. Fine. So which of the following represents the variation of pressure along the axis of the tube? So how the pressure varies? So first tell me. So here the velocity is going to be less, and then here the velocity is more, right? So here the velocity is less means the pressure will be more. Yes. And here velocity is more means the pressure will be less. Yes or no? So I can write like, so initially the pressure is more, and along the axis of the tube the pressure getting decreases. See here. So initially it is more, and for some time it is constant, and then it is getting decreases, here decreasing, and again here it is constant because the cross section is same. So option 2 I can choose. Initially the pressure is more, right? So then it is uniform for some time. Then again from here the cross section decreased, the pressure decreased. So like this, and then so again constant. So option 2 is the correct one guys. Done? Chalo. So hope you guys can solve this question. Let's take this as homework 2. Previously one question I gave it as homework 1, and so this question also you can take it as homework 3. If you are not getting, I'll solve this question in the next session. So but try to solve it on your own. So I am deleting this slide. Chalo. So that's it from my end guys for today's session. So in the next class we'll do some questions on the Bernoullis principle again, and we'll go for the velocity of flux concept. Okay, so till then keep studying. All the very best. Bye.